Welcome to This Explainer. Think of today's session as your personal survival map through the absolute wasteland of tricky exam questions. We are going on a veritable Mad Max Fury Road journey to claim your A-star treasure in Cambridge Physics. Today, we are diving deep into the examiner's playbook to master the spring constant, Hooke's law, and that ever-present, sometimes terrifying, F equals ma relationship. Whether you're tackling syllabus code 0625, 0651, 0652, 5054, or even building foundations for 9702. The strategies we uncover today are going to completely change how you write your answers. To kick things off, let's look at a real Cambridge Physics past paper question for syllabus code 0625 involving a spring system. Imagine we have two students attempting this very question right now. Let's call them Alex and Sam. Now, Alex is the kind of student who overloads their answer with raw physics facts. I mean, they're writing down every single equation they can possibly remember. F equals kx, W equals mg, F equals ma, just throwing everything at the wall, but offering absolutely zero analytical depth to connect them. Sam, on the other hand, is completely rushing against the clock, furiously scribbling away, but completely missing the specific requirements of the command words in the prompt. They calculate a number perfectly, but the question asks them to describe and explain. We are going to put both of their answers under the microscope today. And by the end of this explainer, you will know exactly how to avoid their fate, decode the examiner's true intentions, and claim your treasure grade. So let's pull up Alex and Sam's answers side by side. If you look at our imaginary split screen right now, it is an absolute bloodbath of red pen marks. Just red ink everywhere. But why? Why did they lose so many marks when they both technically knew the physics formulas? Well, Cambridge Principal Examiner reports explicitly show that multi-stage analysis for these specific formulas is notoriously misunderstood year after year. Students constantly treat the spring constant equation and Newton's second law as if they are isolated islands of information. But listen to me carefully here. Examiners aren't just testing if you can memorize a formula from a textbook. That's the bare minimum. They are actively testing your ability to navigate multi-step logic. When Alex writes down an answer, he entirely forgets to define the physical limits of the system. He just writes the math. When Sam rushes, she calculates the numerical value for the extension, but completely forgets to interpret what that number actually means in the context of the physical system provided in the exam paper. So, we are going to fix that structural gap right now. We're going to build a completely bulletproof approach to these multi-stage questions.
Section 1. The conceptual foundation. To secure those top marks, we cannot just rely on superficial breadth. We first need to establish a rock-solid theoretical architecture.
This conceptual foundation relies on mastering what we call the Peel framework. That stands for point, evidence, explanation, and link. Let's apply this to our baseline definitions. The spring constant, represented by K, is the force per unit extension. But here is the crucial, absolute deal-breaker caveat that Alex always misses, and it costs them a whole grade boundary. This formula holds true only until we hit the limit of proportionality on a load extension graph. If you just write down K equals F over X in an exam without explicitly acknowledging that this beautiful, neat, linear relationship completely breaks down once the spring is stretched beyond its elastic limit, you are quite literally leaving method marks on the table. When applying our Peel framework here to structure a perfect answer, your point is the core definition of the spring constant. Your evidence is extracting the data from the graph provided, showing the exact linear region. Your explanation dictates exactly how the force relates to the extension in that specific region. And finally, your link ties it all back to the specific limit of proportionality mentioned in the question's unique scenario. If you structure your thought process like that, the examiner has no choice but to award full marks.
Now I want you to notice the massive contrast between a static system and a dynamic one. This is a huge trap. Examiners explicitly highlight that candidates who reference cross-topic connections, like smoothly linking the static spring system of K equals F over X to a dynamic F equals ma relationship when an object on that very same spring is released, achieve significantly higher scores. Imagine a heavy mass hanging perfectly still on a spring. That's static. Forces are balanced. But the exact millisecond you pull it down further and let go, it accelerates. Suddenly, boom, Newton's second law comes into play. If you can clearly spot in the exam question which part of your answer requires static analysis and which requires dynamic analysis, you are instantly thinking like a top-tier candidate. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, jumping back in. Think about Alex's answer. He completely ignored the acceleration phase. He analyzed the spring as if it were frozen in time, missing half the marks. Section 2, the technical methodology. Now, what's really exciting about this next part is how it transitions us from simply knowing the physics facts in our heads to actually forcing the examiner to give us the method marks on paper. We call this the physics success blueprint. Method marks are your absolute safety net, and you secure them by systematic processing. It follows a strictly standardized 5-step sequence. Step 1, you must actively identify the key elements and, most importantly, the command words. Is the question asking you to state, describe, or calculate? If it says describe and you only calculate, you lose. Step 2, logically apply the relevant physical principles. Decide right then and there, is this a Hooke's law situation, an F equals ma situation, or both? Step 3, execute your analysis with abundantly clear working. Do not skip steps in your algebra. Step 4, verify your results against basic common sense. Look at your number. Does a calculated spring constant of 10 million newtons per meter make sense for a tiny plastic slinky? Absolutely not. Catch your own calculator errors. And finally, step 5, present your answer in the correct format with the proper units. Even if you somehow botch the final algebraic calculation, a perfectly structured method utilizing these 5 steps will salvage the vast majority of the partial marks. Throughout this entire methodological sequence, your critical data interpretation skills are going to be heavily tested by Cambridge. You will rarely just be handed the force and the mass clearly on a silver platter. Life isn't that easy. Instead, you will need to extract the extension values from a complex multi-column data table, or perhaps calculate the gradient of the linear portion of a complicated load extension graph just to find your initial spring constant. This requires you to actively interpret the relationships. You have to look at the graph and say, okay, right here where the graph curves, the relationship is no longer proportional. Hooke's law no longer applies. Drawing evidence-based conclusions means pointing directly to the specific data point in the provided table where the extension visibly ceases to be uniform and stating confidently to the examiner, based on data point X, this is where we have reached the limit of proportionality. Section 3, Examiner Warnings. Stop scrolling, subscribe to our YouTube channel Ace the Exams at @ACExams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @ACExams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's move to the most crucial part of our analysis and see the top 3 red flags directly from the principal examiner reports. Listen up, because these are the top 3 mistakes students make year in and year out. Number 1, being too vague. Number 2, exhibiting poor presentation and forgetting units. And number 3, the most fatal error of all, ignoring the specific context of the question. We are going into our interactive workshop right now. Challenge 1 is our data scan. I want you to imagine a complex physics chart showing varying spring constants for different materials on the screen. We're putting a 60-second visual countdown timer on the clock. Go. If you scan that data and just write down the spring stretches, you immediately trigger warning number 1, vagueness. The examiner is screaming, by how much? Under what specific force? Warning number 2 is forgetting format. Writing an answer of 50 without the Newton per meter unit will immediately cost you the final accuracy mark. Okay, time's up on the scan. Now for challenge 2, let's play Find the Flaw. Listen very carefully to this sample paragraph a student wrote. The force increases, so the acceleration increases because of F equals ma. Did you spot the flaw? I'll give you a second. Got it? It violates warning number 3. It is entirely generic. It completely fails to mention the specific masses, the specific tension, or the specific spring described in the exam scenario. It's a textbook answer, not an applied answer.
This brilliantly illustrates the examiner's ultimate warning. A generic, rote-memorized answer will fail the application assessment objectives. You must always link every single point directly to the provided scenario. Let's say the question is about a bungee jumper. Do not start talking about a tiny laboratory spring mass system. Talk about the tension in the thick bungee cord. Talk about the mass of the human jumper. Talk about the specific deceleration they experience as the cord stretches to its limit. The examiners write in their reports, year after year, that candidates who simply regurgitate textbook definitions without actively applying them to the real-world, messy scenario presented in the paper are severely penalized. You have to prove you can do real physics. Context is absolutely king in Cambridge physics exams.
To prevent leaving out vital context-specific details when you are under severe time pressure, try creating a custom acronym memory hack for these interconnected factors. Welcome to Challenge 3 of our workshop, Speed Writing. We're putting 30 seconds on the clock right now. Your goal is to write one perfect Peel paragraph using our custom acronym, CLEAR. Context, limit, equation, application, result. Go. When you face a spring constant question, run through this checklist in your head. Have I stated the context of the system? Have I explicitly checked the limit of proportionality? Have I written out the correct equation before plugging in numbers? Have I clearly shown the application of the specific data provided? And finally, is my result formatted with the correct significant figures and units? Time is ticking down. 10 seconds. And stop. Taking just 30 seconds to run through CLER in your head will instantly elevate your paragraph from a disorganized, rushed mess like Sam's to a precisely structured, top-tier response.
Section 4, Higher Order Evaluation. Now, to push your grade to the absolute top, we must elevate our approach from simple calculation to critical analysis and higher-order evaluation. This is where we separate the good students from the truly exceptional A-star candidates. The examiner isn't just looking for human calculators, they're looking for scientists who evaluate the physical world. Top-scoring candidates demonstrate advanced evaluative thinking by consistently questioning assumptions, considering alternative perspectives, and meticulously justifying every single decision with physical evidence. Let me give you a concrete example. When applying F equals ma to a mass falling and stretching a spring, an average student assumes the only forces involved are gravity pulling down and the spring tension pulling up. A top-tier candidate, however, questions that assumption. They explicitly write down that air resistance is being considered negligible for the sake of the ideal calculation, but they acknowledge that in reality, air resistance would reduce the net downward force and therefore slightly decrease the acceleration. This level of justification, backed by real-world physical evidence, is exactly what the descriptive, analytical, and evaluative framework of the syllabus actually demands.
When evaluating the quality of your evidence, particularly in practical paper questions, it is absolutely essential to explicitly identify limitations and assumptions, and then logically show exactly how they impact your final conclusion. Let's say you calculate the spring constant from an experimental data table that you generated in a lab. You must identify the limitations of your setup. Was the simple meter ruler used to measure the extension truly precise to the millimeter? Probably not. What assumptions were made? Well, we assumed the spring didn't permanently deform during the previous heavy trial. What is the actual effect on the conclusion? You need to spell it out. If the spring was permanently deformed, the initial starting length recorded would be completely inaccurate. This throws off all subsequent extension calculations, ultimately resulting in an artificially skewed and incorrect spring constant. Detailing this exact chain of thought is how you harvest maximum marks on those tricky evaluation questions.
Furthermore, when a question asks for comparative analysis, it demands much more than just vaguely pointing out similarities. You must explicitly identify differences using comparative connectives to judge their relative importance. This is a massive secret weapon. You should be constantly using words like whereas, conversely, or in contrast in your descriptive answers. If you are asked to compare a stiff spring to a loose spring, do not just say one is hard to pull and one is easy. That's middle school science. Say something like, spring A requires a significantly greater force per unit extension, yielding a higher spring constant, whereas spring B reaches its limit of proportionality at a much lower applied force, indicating a lower elastic limit. By using these comparative connectives, you structurally force your own brain to weigh the physics evidence logically, perfectly satisfying the highest tier of the marking scheme. Ultimately, the Cambridge syllabus prioritizes logical, structured reasoning and analytical depth that can be seamlessly transferred across entirely different topics. Let's recap the final system. The 3 golden rules that guarantee top marks are, number 1, command word decoding. Always know exactly what the verb is asking you to do. Number 2, strict Peel framework application. Point, evidence, explanation, link. And number 3, employing a time management matrix that ensures you don't panic and rush like Sam did, leaving valuable marks blank. Implementing these 3 strategies consistently is your blueprint for success. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. Subscribe right now to at Ace the Exams IGCSE and click that bell. Don't let another exam pass you by. So ask yourself, are you just memorizing formulas? Or are you truly building the analytical toolkit to master any tricky question the examiner throws your way? Are you going to be Alex, overloading on facts without any structure? Or are you going to step up, apply the blueprint, check your assumptions, and lock in that A-star? Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. like, and share this video with a study partner. Ace the exams. Your Cambridge success starts here. Keep analyzing, keep evaluating, and we'll see you in the next explainer.